Yep. Hi, George. Hi, George.
Hello, everyone.
Oh, Hori-san.
Hori-san.
Hello. And Nikolai. Happy to see you. And Yoko-san.
Dobar dan, Nebojša. Nice to see you here. My countrymen. Okay, so...
Oh, Takumi-san, welcome.
Hey, Takumi-san, hello.
Hi, Leah. We're so happy to see you.
こんにちは。
Konnichiwa, Takumi-san.
Okay, so far.
Tanaka-sensei. Yoroshiku onegaishimasu.
Yoroshiku onegaishimasu. Okay, 5 o'clock. I think we can start. Konnichiwa, Nihon. Good morning, Europe. We saw some people signing up from United States. I guess that is very early for them still, but I guess good morning also to America. Oh, hello, Nikolai. Nice to see you. I would like, before we start, to ask, if possible, if you're comfortable with that, to please turn on your videos. It is always much better when speakers can see their audience, so it is much more comfortable to interact. And keep your videos on, if you don't mind, please. So today, we're going to have a very interesting speaker that in Aquaphotomics lab, at least, we know him for a very long time. His name is Elmar Fuchs, and at least on my part, I'm admiring his work for at least 10 years so far. So today, Elmar was very kind to accept our invitation to give a webinar, and he's going to talk about one phenomena called a water bridge, actually. So this is a phenomenon. I think you read in the announcement that he was the one who provided some kind of explanation of what is going on. But this is a phenomenon known in science for at least 200 years, and no one has been able to explain why does it happen, why this water bridge is being formed. And then maybe like now 10 years ago, Elmar decided to pursue this. He was interested in why water bridge forms. And he published a paper about that. At that time, I actually met him at Water Conference, a huge conference dedicated to water science. And this work has been amazing. And he's, I would like to say that maybe Elmar can talk a little bit more about that, but he was pursuing this not as an official project. This started all as just an interest for him, and he was not very much encouraged, as far as I remember, by his community at that time to pursue these studies. So his findings, his research are, I think, a product of his own personal enthusiasm. And as scientist, I very much understand and I support, and I'm happy that this brought some, how can I say, new discoveries. So we're very honored that today Elmar is with us. And he will be talking for about 45 minutes. During that time, if you have any questions, as it comes to your mind, you can type your questions in the chat box, and later I can read and Elmar can answer. After the lecture, of course, we will be open for discussion, during which you just raise a hand or type in the chat box that you would like to ask a question, and then you will have a chance to speak. All the webinar is going to be recorded. You can turn on translation to Japanese from English if you have troubles with understanding English. And after the webinar is finished in a few days, recording will be available on YouTube. And of course, then at that time, you can also post your comments. You can ask other questions if you have, and so on. So now, if Professor Tsenko would like some words of welcome, we can hear from Professor Tsenko.
Thank you, Elena. Of course. First of all, welcome, Elmar. I really thank you for accepting our invitation to give a webinar as well as the lecture you gave to our seminar in Japan, in my lab. I think you're a happy man doing research on a subject that you really love, and being paid for this, right?
Yes.
Yes. So I think your talk will teach a lot of things, and about water physics, and of course we will have many questions, and people will see the potential for development and knowledge about water and water molecular system and optics as well. So thank you again and good luck.
Thank you, Professor
Well,
Tsenko. Elmar,
thank you.
the floor is
Yes.
yours. Thank you very much.
Well, dear Jelena, dear Professor Tsenko, thank you very much for inviting me to give this webinar. It is an honor for me to be here. Thank you very much. It was an honor to be in Japan as well. I enjoyed it also very much. Thank you also for the possibility to talk to you there. And I'm very happy that I again now have the possibility to talk a little bit about a subject that I actually really love. That is true. Just to be clear here, I'm not only doing research on the water bridge. In the beginning, it was the reason why I got my job at Wetsus in the Netherlands, yes, but it's now a part of the research that I do. But I am actually in the position that Professor Tsenko mentioned, that the research that I do, be it the water bridge, be it vortices, be it magnetic water treatment, are subjects that are really close to what I'm really interested in. And I am really doing this with all my heart and passion. So that is true. Now, I guess everybody can see my screen.
Yes.
Yes, perfect. Now, in the announcement, it said physics of the floating water bridge. Yes, but it also, a title like that gives the impression that everything is understood, which in my opinion is not the case. So I reformulated it to an aqueous horizontal electrohydrodynamic liquid bridge, which is more a description of the phenomenon, and I will try to give some answers to the properties of that phenomenon that we have found over the years. Now, I'm talking about the interaction of high voltage and water, and I'm sure, quite sure, everybody of you, at some point in your life, you have heard that these two really don't go well together. Just imagine you have electrical machinery, you pour water in it, it's a catastrophe. Or vice versa, imagine yourself immersed in water, swimming in the lake, and the lightning comes, or you're in the bathtub and you have some sort of electrical discharge there, it can be lethal. So the interaction of high voltage and water is actually very destructive. And when, as a scientist, when you pursue something, you always have to ask yourself, in my opinion, you should ask yourself, why am I doing this? What's the purpose? And I guess the interaction of high voltage and water can be better understood if you take a look at it from a different perspective. For example, from our International Space Station, flying above our beautiful planet, you see that the interaction of high voltage and water is very common on this world. I think every 7 seconds or something you have a lightning discharge, which is nothing but the interaction of high voltage and water. And if nature does this, if this is something that's been happening on our planet for millennia, I think it's worth studying it, because in the philosophy of the Austrian forester Victor Schauberger, in my opinion, it makes sense to understand and copy nature. So from a different point of view, it's very interesting to look at the interaction of high voltage and water. And of course, the discharges like lightnings are interesting to pursue, but even before that happens, interesting things happen to water. For example, the electrohydrodynamic liquid bridge I'm talking about. What is that? It is a phenomenon discovered in 1893 by Sir William George Armstrong. He took back then 2 wine glasses filled with pure water. He had a phonograph generator. I think it was hand-driven. And he was just experimenting with these wine glasses, water and the high voltage. And to his astonishment, he was able to produce a string of water hanging between these 2 glasses once he had applied a high voltage of about 15,000 volts DC. And we can look now with a high-speed video at what happens when you apply this high voltage to 2 beakers filled with water. In the beginning, you see a discharge like a lightning, and then you see that the surface of the water on both sides gets very, very agile and very active. And you have Taylor conformation, you have droplets ejection, so the charge tries to go to the other side, positive to the negative side, and vice versa, until you have a capillary bridge. A capillary bridge is nothing special. It's like a droplet between 2 glasses. You don't need high voltage for that. But once you have a capillary bridge and the connection is formed, within a few fractions of a second, this bridge will gain volume. The water flow in both directions will increase, and you have a macroscopic watery connection between the beakers, and that is the phenomenon we're talking about. This is the water bridge. Now, if you take a look at this phenomenon with a normal camera from the side, as we see here, you will see that the formation that I've just shown you in real time is very, very fast. Now we're applying the voltage, capillary bridge, and here we are. And you see that immediately that there is a water flow here from the right side to the left side, from the anode to the cathode side. And when we now pull the beakers apart, this is where the interesting part comes, we see that this bridge interestingly remains stable. In the beginning, we thought it's like a cylinder. It looks also like a cylinder, but if you extend it a little bit more, you're seeing it hanging in there like a rope of water between these 2 beakers. And apparently there's water transport going on. From this video, at least we see from the right side to the left side, but in reality, it's actually in both directions. We can visualize the flow in the water bridge by a very simple method. We add tracer particles. We do again a high-speed video, and we see that the water in the bridge is not flowing directly. This is not a laminar flow, but actually the bridge is rotating. So we have a spiral-like flow in both directions, which is not directly obvious from this video because the tracer particles are only on the outside. If you want to look into the bridge and get an idea about the flow, this is more difficult. We did this by putting the bridge setup into an MRI scanner, and then we could get a 3-dimensional flow, a visualization by MR phase contrast imaging, as you can see here. And you see this is like 2 spirals that are intertwined, that are showing that you have spiral flows against each other from anolyte to catholyte and back. So you have an equilibrium and the water bridge does not overflow. Now, from a field point of view, if you do an electric field simulation, very, very simple 2-dimensionally field simulation in COMSOL, you can see that just by a very crude approximation, you have forces that pull the water into the bridge and from the bridge into the beakers, and also forces that make sure that the bridge does not break down, because water is has a permanent dipole and is drawn to the points of highest field strength. So we get a rough idea why the bridge is stable. You can do this also a little bit more complicated when you add the Navier-Stokes equations and the Maxwell stress tensor. Then you get a nice, also in this case, 2-dimensional visualization of the flow in the water bridge, which nicely coincides with the flow in the actual phenomenon. And the simulations allow you to use different liquids as well for your simulation, for your calculations, because what goes in there are actually just a few numbers, like the conductivity and the electrical permittivity. And that very early in our research, it brought us to the question, is this a phenomenon that's only possible for water, or can you do bridges with other liquids as well. And yes, you can. Any liquid that has a sufficiently low DC conductivity and a permanent dipole moment can form a liquid bridge. However, if you're doing this, for example, with the alcohols as shown here, you have to be very careful. Remember what I showed you, the beginning of the bridge and how it forms, that in the beginning there's a discharge. So if you don't do this under a nitrogen atmosphere, it's very easy that your setup starts to burn, and naturally you would want to avoid that. From all these liquids that I've shown here, glycerol is the most interesting in my opinion. We are working with glycerol here with a different setup where we had the electrodes very close to each other with a spacer in between to prevent electrical discharge. And why am I showing this to you? Because when we turn on the high voltage here, we see the liquid, the glycerol, by the way, also with tracer particles, is drawn to the electrodes. And glycerol allowed us to do something that is impossible to do with water. By lowering the Q width after applying the high voltage, we were able to separate the bridge from the beaker, so to have a pure bridge of liquid of glycerol here floating between the electrodes. And also with your naked eye, you can see that the viscosity of glycerol seems reduced here. It seems very less viscous than the normal state, and also this bridge here is rotating. With glycerol, we also did an NMR investigation. So the MRI scanner that we used had the possibility to do NMR spectroscopy as well. And here we found out that the applied high voltage had no effect on T1, the spin lattice relaxation, but it did have an effect on T2, which does represent the local entropy of the system. And now there are a couple of possibilities how to interpret these results. We interpreted it as pointing towards a proton population in electrically stressed glycerol that is more mobile that we found in the bulk. And we could do this because we had a similar finding previously published and found for water. Protons in water, if you have a water bridge, come from the fact that when you apply high voltage to water, which is quite obvious, you get electrolysis. Normally in pure water, you cannot have electrolysis, but if the voltage is high enough and you overcome all the overpotentials, then you can have it. What you see here is water with the addition of a pH dye. Because of the saturation with CO2 from the atmosphere, it's not green, it's yellow, so we have a pH of 5.56. And as soon as we have the bridge, you can nicely see on the left side around the electrode, it's getting a little bit red, but on the right side is getting a little bit green, so you have the proton formation on one side and hydroxyl ion formation on the other side. And because the protons are much more mobile, because they're lighter than the hydroxyl ions, there's an imbalance here, meaning that the recombination to water does not happen in the bridge, but in the catholyte beaker. This is also why up here on the right side, it stays yellow and it's never really gets green on the left side. We could also simulate this electrolysis using the result from the simulation I've shown you before. And you can see, because the protons are more mobile here, nicely also reflected in a simulation, you have a recombination to water here in the catholyte. So that we understand, we have a production of protons and hydroxyl ions, as you can see here. We have a liquid flow due to electrohydrodynamics. And of course, we have a gas flow. I did not mention it, but we could also measure that. So we actually have high voltage electrolysis happening here. Interestingly, if you look at the ion flow, again, the protons flow here from the right side, from the anode to the cathode. So you have a monodirectional proton flow, although the water is flowing in both directions. And this is interesting because this is actually looking like an electrical circuit here. It is an electrical circuit. And you're putting a lot of power in there because you have got 20 kilovolts and 0.5 milliamps. So this is actually like, if you will, like an old bulb with a wire, just that our wire is here made of water, and it's emitting infrared radiation, of course, as you can see here when you look at the system with thermographic camera. It's heating up to about 40 degrees Celsius. This emission was very interesting when I showed it to Professor Friedemann Freund from NASA Ames some years ago. He said, Elmar, we have to look at this and we have to compare it, the spectrum, to the emission of normal water, because he was thinking that it would be different. So let's first take a look at the emission of liquid water at temperatures in this range. So we have 37, 47 degrees here. Of course, we have a CO2 absorption peak. We have water vapor absorption here. And the temperature, of course, is the integral below the curves. So we have a bigger area here below 47 degrees and a smaller area below 37 degrees. The water bridge is here, this purple curve. What's probably catches your eye first is that the vapor here is emitting. This is because we have ions in the air that collide with water molecules and allow here small vapor emission close to the bridge. But this is not as important as the fact that we have here in the long wave, in the short wave region, the intensity is higher here than in the shortwave region. If you take a look at the curve of the water bridge, there seems to be an extra intensity at about 2,150 wave numbers. So the area here is more comparable to water at 47 degrees, whereas the area here in the long wave region is more comparable to water at 37 degrees. And that means if you take two thermographic cameras, perfectly calibrated, you look at the water bridge with both of them, you see two different temperatures. And this is possible because temperature is a parameter that is defined for systems being in equilibrium, and the water bridge is not. So, of course, the water bridge doesn't have two temperatures at once. It just has an extra emission at a shorter wavelength. And Professor Freund said, Elmar, I'm sure this is a result from a protonic band transition inside of the bridge, because Professor Freund is still working with rocks and proton conduction in rocks, of course in solids, and he can predict earthquakes from the proton currents that are released there due to the pressure. And he said, I think, Elmar, you have a sort of proton conduction band in your bridge, and this is why you get this transmission here from n=2 to n=1. And I said, Friedemann, this is interesting, but for a conduction band, we would actually need some sort at least of long-range order, and in liquid you don't have that. And back then we were still discussing what would happen to the bridge, but to the water in the bridge due to the high voltage. Would there be an ordering of molecules? Where we very quickly found out that this was not the case. The voltage was way too low for that. But just asking experimentally the question, in what state is the bridge, in what phase, with it ultra-fast vibrational energy relaxation with Haube-Backer in Amsterdam. What is that? We took an HDO molecule, we made HDO molecules in the bridge, and then we excited the OH bond with an ultra-fast infrared laser. Why would you do that? Because if you excite this and then you probe the vibration and see how long it takes for this vibration to stop, you get a pretty good idea in which phase you're in, because in the solid phase, this proton is very strongly bound and the vibration stops much faster than in the liquid phase. It's easy to put some numbers to this. Ice at 0 degrees, for example, has a relaxation time of 384 femtoseconds, whereas liquid water, so after you melt it, same temperature, you have the phase transition, it jumps up to 740 femtoseconds, because, as you know, water is either solid, then it's ice, or it's liquid, but there is nothing in between. This is a first order phase transition. We were very astonished to find that the water bridge, which was suspected to be somewhere up here, 800, 900 femtoseconds, was actually in this phase transition. And that means that the OH, vibration relaxation was happening at the time that was not present in any liquid or solid state known, meaning that in the phase diagram, doesn't matter which temperature or pressure you use, you can never get here because you're always either liquid or solid. This is actually just inside of the small line between the phase transition. So the hydrogen bonds are stronger than in liquid water, but weaker than in ice. Another fact that we got from this measurement is that the thermalization dynamics is slower in the water bridge than in normal water. What does that mean? Now, on the one hand, the energy from the molecule to its neighbor is passed on very fast, so there's a strong bond, but the spreading of the energy throughout the system is slow. So it looks as if there are some regions, some domains where something is happening to the water molecules so that they are more strongly bound. But this is not happening throughout the system. This is just happening in certain regions. So similar to a second order phase transition, if you will. We tested these results by doing a completely independent experiment, which was called quasi-elastic Newton scattering with Professor José Teixeira in Saclay in France. Because if you have more strongly bound water molecules and you're thinking you have some sort of proton channels or proton bands, you should have an increased proton mobility in the bridge. And what you see here is one of the raw data results where you have the energy of the neutrons. So you shoot neutrons at the system and you look at the energy that these neutrons give to the protons or that they absorb from the protons. And the broader this energy, the more mobile the protons are. And here you see the green curved water bridge. This is much broader than water in an aluminum cylinder, which we used as reference. If you do the evaluation of this data, it was difficult because we had a shadow in the system due to the setup, and the data was also very spread very broadly. But nevertheless, we could show by standard evaluation that we have a diffusion constant that was much higher than that of normal liquid water. So we had a higher mobility of protons in the water bridge as we suspected. And next to these measurements, that the evaluations of which contain many assumptions. So we thought, wouldn't there be a possibility to directly observe this proton flow, and so they have a more clearer view on what is happening? And for that, we used a shadowgraphy setup. That's a very simple thing. You have a camera, a light source, a beam splitter, a retroreflector, the high voltage source, the beakers, ground and high voltage, and the bridge in between. And what happens? Light comes, goes through the beam splitter onto the retroreflector, through the bridge, goes back, and then to the camera. Now, in a normal visualization, just to give you a short explanation, even we have refracted beams, the camera is normally positioned in a way that it nevertheless hits the sensor. If we were very precise here scientifically, any shadow you see in this image on the right side is also some sort of shadowgraphy, because these dark spots here and the transparent material are exactly due to that fact that you have some lensing effects from refracted beams that do not hit the sensor. In the shadowgraphy setup, you enhance this. So the same system in shadowgraphy is much darker, and you're much more sensitive to changes in the refractive index. And just to remind you, if you have a normal visualization of the water bridge and you start it up and look at the beakers, you see that once the water bridge has formed, it is a very transparent, very clear phenomenon. So with the naked eye, you don't see anything here inside of your bridge. As you might have suspected, if you do this in shadowgraphy, the situation is different. But the beakers are darker, but as soon as we start the bridge, it's very interesting to see that you have got shadows inside of the bridge. By the way, you also see shadows and schlieren here in the beakers. This is because you can nicely visualize also where the warm water, because the bridge heats up, is mixing with the colder water inside of the beakers. And also, if we now extend our bridge a little bit, you will see that this shadowgraphy tells us that there's something happening inside of the bridge that changes the refractive index, because we clearly see there are shadows but being formed and moving. But with this normal video, we cannot say anything about the movement. For that, we again would need a high-speed visualization. And if we do a high-speed visualization of the shadow rings, then we see that they're coming from the right side, from the anode, and that they're moving to the left side. And we know that, yeah, we have also surface reflection here and focal caustic here. And we know that shadow rings mark regions of a different refractive index. Refractive index of water can change due to many reasons. Most probable are density gradients due to temperature or local changes in polarizability of molecules or molecular clusters. For example, if you have bulks of protons, that would also change the polarizability. Now, if we look at the temperature again, we did this before, now we have a magnification of that video. You see that indeed, of course, we have a temperature distribution in the bridge, but the dynamics looks very different from these shadows, and also the time scale is different. So whatever we see here when we're looking at the shadow rings, it cannot be the temperature distribution. So let's assume we have changes in polarizability. If that is true, then laser light should be scattered when illuminated from the side. So you would expect to have Rayleigh scattering. And this is what you see here nicely. You see here, we're shining a laser beam from the side. You have the bridge here. You have droplets, by the way, flying here above and below. This is also a nice side effect. But most importantly, we see the laser here because we have scattering. Otherwise, we wouldn't see it. So that's a nice confirmation. And then let's look at the shadow rings again. If we think these are somehow linked to our protons, first let's analyze the velocity and their frequency. Now this can be simply done with a time-space diagram here, and we can easily measure that the velocity is about 32 centimeters per second, and we have seen they move from anode to cathode, as the protons. They also do that. So let's test the hypothesis that the rings actually visualize the proton movement. And for that, we would have to compare their velocity of the protons microscopically to the macroscopic velocity of the rings. Now, when we calculate our proton mobility from the quasi-elastic Newton scattering results, we get a value that is very close to that reported by other authors in the field of electrohydrodynamics as anomalously high charge mobility. So in these publications, the authors do not talk about the nature of the charge carrier. They're just talking about charges. And as you can see, the proton mobility that we calculate is almost exactly the same value and twice as high as the proton mobility in normal water. So if we now assume that we have normal water and this electrically stressed water in the bridge, we should have then a total velocity that is somewhere in between the velocity of the protons in normal water and that of this new phase, because as I told you, it's not the total, it's with the when I told you about the phase transition, I said that it's not all the water that goes into this phase transition, but it's a part of the water. So we would assume that we have a velocity that is in between that of the normal water and the electrically stressed water. We have an electrical field that drops with 5,300 volts per centimeter. We measured that and we also simulated that. And we would have proton velocities 50 centimeters per second for the enhanced mobility of the new phase and 25 centimeters per second in the bulk. We know that the shadow rings move at 32 centimeters per second. And this is great because this is exactly what we would expect. So it's faster than in normal water, but it's not as fast as if the whole bridge were already in this new phase. We have an onset of the phase transition. Some parts apparently of the bridge contain this coupled water with stronger hydrogen bonds and other parts don't. Then we have to answer the question why there is a frequency when we apply a DC voltage, because you don't expect that. And this has to do with the fluid dynamics of the system. Whenever you have shear layers in fluid dynamics, you create vortices, as you can nicely see here in this image, where you have colder and warmer layers in the atmosphere passing each other, creating these beautiful cloud vortices. We have the same here in the bridge, and fluid mechanics tells us that if we make a couple of assumptions, we should have a frequency here, vortices occurring at about 100 plus minus 50 hertz, and our rings appear with a frequency of about 100 hertz. So we have the rings because we have bulks of protons entering the bridge with a 100 hertz oscillation. Whenever we have these protons, they change the polarizability of the bridge, and therefore it makes a nice dark ring. So we understand a little bit protons, we understand a little bit the optical properties and how they are coupled. What I haven't talked about is what actually is this electrically stressed phase of water. Why do the protons move faster in there? And in order to understand that, we did a different experiment. We did Raman measurement of electrified water with a cuvette and a needle and a plate in the bottom. Why did we do this? Because in the water bridge, as you have seen, you have electrohydrodynamics, you have electrochemistry, you have electrolysis happening, and apparently you have some direct influence of the electric field on the water molecules. It's all coupled, and that makes the situation complicated. In this setup, we took the electrical field effect out from that, and we're only looking at what happens now to the water molecules if we apply a strong electric field. There's no electrolysis, there is no hydrodynamics. We did this with Raman spectroscopy. So we had here the cuvette with the green laser at 540 nanometers. And if you take now an image of this cuvette through your alignment goggles, you still see a little bit of the green light that is passing through these goggles, but you can nicely see with your naked eye the Raman scattering, here the Stokes line at 625 nanometers. And it's very easy to do spectroscopy, of course, on this line. Now, it is very important here to understand that we are not seeing and expecting any change in average structure in the water bridge. In my opinion, structure is a very bad parameter for a liquid, because this is a parameter that tells you something about the system that does not change like a solid. We know that in liquid water, we have femtosecond changes of the water, of the hydrogen bond bridges between the molecules. So an average structure does only tell you so much. It's much more interesting to look at the dynamics and not as much as the structure in the bridge. So if we would have a change in average structure, in order to get that, you would have to have 1,000 times higher voltage. And if you apply that, you have a dielectric breakdown. So you can't have that. There's no change in structure. What actually happens, and this is what makes this so interesting, in my opinion, is that you break down the symmetry of the space. So whereas without an electric field, the water molecule, a dipole, can vibrate and oscillate in all directions. It's degenerate, it doesn't matter. You apply an electric field and all of a sudden the degeneracy is lifted, and it makes a difference for the water molecule in which direction it turns, in which direction it vibrates. So you have a broken symmetry. And what happens if you have that? Well, a mechanical analogy is the Euler-Strutt problem. We have a very high symmetry in the beginning, then you break the symmetry, it's broken, and you have a new ground state that is lower in energy than the original state. You can also see this in molecular dynamics. When you apply the electric field, the rotations are no longer degenerate, and a higher probability of vibrational coupling, of phonon coupling, occurs. This was actually calculated and predicted by Elton and Ferrand in their nice paper in Nature Communications. And they said that they find the lowest frequency vibrational Raman peak is about 435 wave numbers, is a transverse optical phonon-like mode. So phonons are coupling, meaning that we have water molecules that do the antisymmetric stretch vibration. And because of the electric field applied, these vibrations now suddenly can couple. And just a short reminder of what are phonons. Phonons can thought to be as quantized sound waves, similar to photons as quantized light waves. And of course, in water, phonons and photons are always coupled because water is a dipole. So whenever you have some vibration there of the dipole, there's always an electromagnetic field involved. So what I'm saying here is that through this coupling of the vibrations, you do not get a change in average structure, but you get a change in the four-dimensional structure because you get phase-correlated oscillations. The late Emilio del Giudice had a wonderful analogy for this. Please allow me to quote him here. He said, Elmar, it's like looking at people in the ballroom. And when there is no music, they are just moving randomly. And then if you would take a picture and you would average them out, you'd get their average distances, etc. But once you turn on the music, all of a sudden everybody is dancing and moving in phase to the music. And he said the music is like the electric field. Again, an average picture would probably give you very similar results to the random situation. But the dynamics, the movements is very different. And so you always have to look at the dynamics of the water rather than its structure. And this is what I mean here by a partial four-dimensional ordering. It's like it's also called in the newer literature a time crystal, which you can see here. And this is something we could see with the Raman spectroscopy. This is why I'm showing this to you. So where we have bulk water, we have, of course, here the excitation and then the emission of the Stokes line at 3,400 wave numbers. If we have the phonon coupling, then we have two additional lines at the distance. We should see some at 435 wave numbers distance. And as you probably expect, we did find these lines experimentally at exactly where they're supposed to be, 430, 435 wave numbers from the main line. So we have an enhanced phonon coupling due to the electric field, due to the broken symmetry. But this we could see at the millimeter distance. So this is a macroscopic phenomenon, not only in the nanometer scale, but this is happening here in the cuvette when you apply the electric field, a distance of millimeters. Finally, if this is really a second order phase transition, we had long discussions about this with Giuseppe Vitiello, who helped us with the interpretation. And he said, you should also see something like the null spike. So a spontaneous symmetry breaks creates an abrupt event due to extreme spatiotemporal localization, a sort of singularity that constitutes the emergence of the new phase. And if we now consider this a second order phase transition, so not everything, it's gradual, it's not happening all at once, but you should have some points where this second order phase transition starts, and we should be able to see this in the water bridge. And for that, we used crossed polarizers and a normal photographic camera because the intensity of the events that I'm showing here is so low that we couldn't do this with the high-speed camera. So these are extremely fast white lines that we see here. Again, these are not the shadow lines, but these are, again, a different phenomenon, different time scale. It's also much finer. And we think that what we see here, changing of the polarization angle of the light, very localized, very fine. We think that we found here these null spikes. So whenever we see when these lines occur, you have an onset of this new electrically stressed phase of water. So summarize, we have understood the water bridge is an electrohydrodynamic phenomenon. Electrohydrodynamics nicely explains the bulk properties of the bridge. We can simulate and show it's a high voltage electrolysis system with the bridge being a proton resistor with enhanced proton velocity due to the phase transition. The electric field triggers the coupling of vibrations. Symmetry breaking takes place, resulting in a second order liquid-to-liquid phase transition. And this new phase is dynamically different because of the coupled phonon modes, but shows roughly the same average structure. I say roughly because we've only published one paper on this. We have data also for measurements in Oxford with Alan Soper and PSI in Switzerland, which is only published, unfortunately, until now in ArchiveX, which shows that there is might be a small difference, but the models that were used to calculate the spectra from the data had difficulties, so we are not sure about that. It could be that there's a small change in average structure, but much more pronounced, of course, is the change in dynamics. And the different molecular properties of our new phase here, we probed with ultra-fast bump probe spectroscopy. So we saw stronger binding of the molecules to its next neighbors and a longer time that it took for the energy to be dissipated throughout the system. And we did quasi-elastic Newton scattering, showing that indeed we have a higher mobility of the protons in these coupled molecules. So when they can be delocalized along a couple of molecules, at least that's our theory. And the vibrational coupling extends over macroscopic distances and therefore results also in different macroscopic properties like change in the index of refraction. And these changes can be visualized by shadowgraphy and polargraphy, to name a few. This research was made possible by Wetsus, the European Center of Excellence for Sustainable Water Technology. I'm very happy and grateful to the companies in the applied water physics team that contributed. Adam Wexler, who did the PhD on the floating water bridge. Some of the data I've shown is from his research. Professor Jakob Boysenschläger from TU Graz, my mentor, who has been accompanying me and helping me throughout my career with, who is the big physicist behind all of this actually. Of course, Professor Friedemann Freund, Emilio Del Giudice, Professor Vitiello, many more. Who made all this possible. Also, this list is not complete here. And of course, I thank all of you very much for your attention. I would be happy to answer any of your questions. Thank you.
Thank you, Elmar. It was really nice to hear this again. I actually felt like I'm listening this. I don't think or maybe I didn't listen carefully when I listened to you when you've been here in October. Now it felt again somehow new, or I heard stuff in another way. So thank you very much. It was very nice to hear this. We are open for questions. Whoever wants to ask something, you can raise your hand. And we have lots of actually comments. I'm not sure if those are questions from Pierre. And Pierre sort of like wrote a paper. I don't know where to begin with. Perhaps
start with the questions, I would say, if there are any.
So I assume you used distilled water. You said you used pure water, right?
Pure water. You need to use pure water. You see, if you add ions, additional ions to the intrinsic ions, H+ and OH-, then these ions have strong local electric fields, and these fields interfere with the outside field, make it more difficult, in our opinion, for this coupling to be established. And also a very practical reason why you shouldn't use ions is that you increase the current if you increase the electrical conductivity and therefore the power output. So a little bit, few more ions and the bridge boils very quickly and you cannot establish the phenomenon. This has to be very cured.
I think your actual presentation answered this first question. How would you see that the current can form without ions? You actually said that those photons form.
Yes, and never forget, water contains ions in its natural state. You have autophotolysis, you have H+ and OH-, so you have small conductivity, even if you would do this without CO2 in nitrogen atmosphere, which we did as well, even then it works. But of course, in our water, we have a little bit of bicarbonate ions, protons extra because of the CO2. But then you have electrolysis, OH-, H+, and you have your ions.
And that was actually very nice to see. This is maybe why I had a feeling that I'm listening again, something new, because recently we did some work on a characterization of water, which is created through the process of electrolysis. And it was very interesting to see this, to connect with what you talked about. The next question, I think also you answered in your presentation. Can we deduce that the floating water bridge is nothing else than liquid ice? Well, it's
what is liquid ice? Ice is solid and water is liquid. So I would say liquid ice is a contradiction in itself. So I would say no, we cannot do that.
No. Let's go in a discussion here, because I think the listeners have to be well informed about water being a liquid crystal. And it's well known, proven, and the spectroscopy that we do also shows this. I was listening to Elmar, and I was thinking, we have beautiful spectra of water showing various structures. Water is liquid, yes, but in the liquid you have at the same time vapor, ice, and bulk, and many other different structures that are changing. And
yes, extremely fast.
Yes, so liquid crystal is water is a liquid crystal, but now the problem is that we talk about different parts of the water being liquid crystal, and different ratios between those phases. So that I think it's a proper way to talk about water. And when I was your system is so beautiful to be monitored by an infrared, because then you can follow all these different structures in the water, changing with the time, because water is a self-organizing system. So obviously the dynamics is always bringing the water to a balance. So
yeah, this is beautifully said. This is what I wanted also to say to you, Elmar, as a comment. What I again felt very new, usually very new in your presentation now compared to the other talks that we normally hear, is that you're actually pointing out, emphasizing another dimension should be really added, which is time. So that is why it is not just structure, it is how, especially with WaterBridge now, this comes, this phenomena is obviously a result of what is going on over time. It's not just a point in time. Yeah, so that was beautiful, actually. And this is, I think, quite unique at the moment. It is not so emphasized enough.
Well, it's the model, if I may, of Emilio del Giudice and Giuseppe Vitiello. They had the idea of coupling. The theory is worked out by them. What we did is that we experimentally found something that can be interpreted more easily in that direction. Not saying we've been proving it, but it's quite obvious that this is a very likely explanation that you have this coupling. But it's not our idea. It's by Emilio del Giudice, Giuliano Paparata actually, and Giuseppe Vitiello.
Just one more comment I want to address by Pierre, and then I will give you a word, Nikolai. I'm sorry for waiting. This comment also and question is interesting. Pierre says, would you consider time crystals as the result of coherence being a manifestation at the particle level? Will the driving mechanism must be the wave property of the water molecules? So maybe Pierre can actually formulate this a little bit better if he's here, because the wording is a little bit tricky. But I like it that he says time crystals, just like you said. Pierre, are you here? Can you just formulate your question better? I don't understand what you actually want to say.
Yeah.
Well, obviously,
I could answer anyhow if you want to.
Okay, sure, absolutely.
In my opinion, time crystal is a modern accepted way of talking about coherence domains. So time crystal in water, the coherence domains, it has been my experience that when you try to publish your data and you talk about coherence domains, you get very unscientific responses very often from reviewers. Time crystal that describes exactly the same phenomenon, but on a broader, it's not only in water, but in a broader material sense, then you can get more easily published, but it's the same thing. So you could say coherence domains are time crystals in water.
Okay. Lovely, lovely said. Thank you, Elmar. Nikolai, please go ahead.
Thank you, Elena, and thank you, Elmar, so much. It's good to see you again.
Good to see you.
I mean, for me, it's all coming together for me now. I just realized that it's exactly on the day 10 years ago that I visited Professor Giuliani, Livio Giuliani, that we had as a speaker last month here in his lab in Rome. And at that time, I was a DNA researcher, having just come across Luc Montagnier's work that we all know, or many of us know. And via Professor Vitiello, he told me to go and visit Giuliani, and I went to his lab. And the first thing Livio told me was, yes, Nikolai, there's something about Montagnier's work and DNA and so on, but first we have to look at water. And at that time, I was like most people, what do you mean water? H2O? What's so special? And then he basically he did like this, shh, just come here, we go to my lab next door, and he showed me the floating water bridge experiment.
Oh,
so
cool.
From that
Livio.
time on,
Yeah.
Livio did, yeah. You know, I thought that DNA was the most important molecule for understanding life, but I'm not so sure anymore. I think it needs to include water in that equation. So thank you very much for
Well,
so my question is, and so now we talk about how we can do the water bridge and macroscopically, but if we take the parameters, like you mentioned, something like I think 5,000 volts per centimeter. But if we look at the cell and the cell membrane,
oh yes,
we also have electric potential, maybe 100 millivolts, a few nanometers. We also get that kind of electric field strength.
Yeah. I always mention that when people ask me, well, this is good for it. It looks nice, but this is very exotic phenomenon. It's not happening nowhere in nature. They say, no. It's happening in each and every cell in your body, where you have the same electric or even high potential, and the same electric field strength, and also proton conduction. It's like a magnification, if you will, of the water channels, if you want, in the cells. And it's also possible that there's a coupling not only across these channels, but also amongst them. It's like a holistic approach to the living body, where the sum of the molecules is less than what the body actually is. So because you have an emergent property, this coupling actually it's I didn't say this in detail, but this is it's a Bose-Einstein condensation of vibrations here, and you have something new that is only possible because you have a coupling of many molecules. And this is also, in my opinion, what's happening in living systems. So you have sum of all the parts, but what's emergent then is something that's only possible through the combination.
Thank you. Yeah.
Thank you.
Thank you, Nikolai. What you just said, Elmar, also addresses some of the comments that Pierre put in the chat box. He was interested in, can you envision, is it possible to envision the same principle of action in biological tissues, in cells? It just was what you said.
Emilio del Giudice told me, Elmar, the bridge is a meridian taken out of the body and magnified. I don't know whether this is true or not, but I remember him telling me that.
Yes, it is difficult to visualize or even think of the methods that can do something like, to investigate meridians. But I liked what
I'm not a medical doctor. It's just repeating that. And
I like how you presented in your lecture. I mean, you saw, I can see that you, with each step, okay, I tested this, I looked at this aspect, then this opened a new hypothesis or a question. So then I took this method and I analyzed this, and this was I really like that about your research. And I can only conclude that, you know how to do many things, you and the people who worked with you. It is beautiful. But it would be really nice to also see near-infrared spectroscopy. I would like to ask.
I agree.
You would. I actually checked with some people if we can do near infrared. It's a little bit tricky to organize how to do the near infrared imaging of something that is, like produced by introducing high voltage. So that's a little bit tricky, but we might find a way. I hope so.
Yeah, you can imagine how tricky it is to be close to a nuclear reactor and handling equipment with high voltage in the sample chamber. So yes, it is, but I think it's doable.
I also.
Let me add something to this, Elena. Can I say something?
Yeah, absolutely. Just go ahead.
Regarding the infrared light, it is a sunlight, Elmar. So it is not something to be afraid of.
I'm not afraid of near infrared.
But
you're not a vampire to be afraid of sunlight.
It would be very, very interesting. I've been dreaming of having a confocal infrared microscopy that can go and probe step by step in depth your system. And even a confocal imaging system will be very, very nice for this system.
I agree.
Then we'll know exactly how different layers are structured.
Yes.
And then we can figure out what exactly. I was following Pierre's comments, and that because the system is so rich of different phases and different molecular structures. So I think your opinion about the structure is a little bit different from what we see. In water, being a very dynamic system, in order to be self-sustained and self-organized, it is always moving, restructuring, but it doesn't mean that. It means that you have numerous different structures at the same moment, right? And then we can probe these structures with light at different frequencies. And those different frequencies are showing, proving the existence of different structures that we already know. We can identify, and also including liquid crystals, including water solvation shells, for example. Exactly already known structures. So we're interested in this in your work because it will be very, very useful system to look at, and a good motivation to develop a new infrared device. Yeah.
Well, I would be, as you know, I would be more than happy to do a joint experiment. It would be really great. And if there's any possibility, please let me know.
Have you tried? You have tried. And you started. You showed the glycerin results. But what is your impression and knowledge and about probing different systems? What is how do you compare water to all these different systems?
Now, to be honest, when the question came up, we tried all the liquids that we can think of, because we suspected you need certain basic properties for the bridge. And we also suspected back then that you might need free protons. That is not true, actually, because with DMSO, which we don't have any protons available, you can also create a bridge. And there are some papers actually in DMSO bridges, not by us, where there is a quite different mechanism of conduction suggested by the authors. And since I have been working on the bridge as an employee of the Excellence Center for Water Technology, our focus has been on water. It would be difficult, seriously, to justify using another liquid for other reasons than for comparison, just to show that it's possible. But because it's more dangerous, most of these liquids are inflammable, and we did have burning beakers. You don't want that. It's more dangerous. And our focus is water more than the bridging phenomenon, we said that we would stick with water and rather change the setup, for example, to the needle plate experiment with the cuvette, but understand water better before we are looking into bridges of other liquids, because then that would be endless. Probably every liquid has, again, different properties. The most intriguing finding is that we did find a substance where the bridge is actually cooler than the liquid in the beakers. Most substances, the bridge heats up, but in 2-propanol, the bridge is the coldest part of the system. I can send you also the paper on that, which is interesting because apparently also this energy dissipation distribution is naturally dependent on the liquid that you use for the bridging.
Wow. Wow. When you said this about propanol, I thought that, wow, this is crazy. It just opens like, why on earth now this particular substance creates colder? Amazing. I want to just comment quickly something about what Professor Tenko also said, and then Wieland, I will give you a word. I was interested lately because I'm interested in what is the origin of information that we see in near-infrared spectra, because I see that near-infrared spectra have more information than other types of spectroscopy. And I was looking recently because I always thought this is why the hydrogen bonds influence this strength of covalent bonds. So this is why I have this different shape and so on. And then I was like, okay, but I don't have only water, I have other liquids. I can try to see how other liquids behave. And I was thinking about DMSO to see, because it does not have this. So, I mean, I don't have yet time, but I was however, within all these liquids, it is obvious that nature, for some reason, favorites water. So I would be interested also to see what is so special about water. Why is it why is it a chosen liquid for this kind of reactions in the body? What is and speaking of that, I thought that there is maybe something like a connection where I would like to ask you a question. This is horizontal water bridge. What about the vertical? Or
we have a paper
Yeah.
on that. You can do vertical water bridges. They don't look as impressive, and the dynamics is different because the gravity then obviously plays a role. But with a setup where we had 2 water reservoirs above each other and small openings, we could actually make a also a vertical water bridge.
Wow.
What is it? Yeah, I can also send you that works. It
Yes,
is interesting,
please.
but of course the shape and everything is different because obviously gravity it plays an important role here. And
that would be so beautiful to see. Oh my God.
And your comment
Bridge.
about your comment about why water. I like what Herbert Bakker, the professor from Amsterdam, says. He took a glass of water and said, you know, Elmar, the bonds, the hydrogen bonds, are partly covalent, so it is absolutely justified to say this is one giant supermolecule. You can consider a glass of water as being one molecule, and this is what. Yeah, it is scientifically correct, but not really. But to some part, it behaves as one molecule. So I think it has both the stability and the flexibility that are required for living processes and for living systems.
Thank you, Elmar. I'm really happy I got the chance to ask you. I'm sorry, Wieland, I saw that you have a question. Please go ahead.
No worries, thank you. But I think Nikolai was before me with raising his hand.
Okay, Wieland, you can.
Okay, thanks. So thanks again for the opportunity to join this webinar. And also the floating water bridge was one of the first experiments with awaked my interest in water. So it was very fascinating me. And I can remember that it was suggested that I read somewhere that it was suggested to use the water bridge as small cell molecular cell biology lab. Are there any experiments or publications about that?
Yeah.
Yet?
Yes, we have been working with water bridge and biological systems in the sense that we put microbiology into the water bridge. We have 2 papers with bacteria and other microorganisms that are exposed to the water bridge, and we have some hypotheses about what happens, because if you ask a microbiologist, the first thing they will say is that, of course, you have the osmotic pressure difference. That alone will kill everything. And high voltage is used for disinfection. So actually, all the bacteria should die immediately. Again, Milo Del Giudice and Giuseppe Vettuelli were the first to tell me, Elmar, do the experiments nevertheless, because we think your bacteria won't die, they will like it. And I remember a water conference in Vermont where we showed the first poster. We didn't have publication yet on this, and Emilia was so happy because we could show that certain bacteria, not all of them, actually, after being exposed to the water bridge, if you cultivate them afterwards, they grow much faster and have an enhanced metabolism.
Wow.
Fact that the reason for which we don't really know. We have some hypotheses in the paper. This is in Biophysical Journal of Biophysics. Anyhow, if you're interested, I can send you the paper. And later on, we found out that some organisms do indeed grow worse. Some die mostly, but some are enhanced in their metabolism after being exposed to the bridge. And we never continued that research line. But yes, there are 2 papers on that.
Thank you, Elmar. Wow. Interesting. Okay, Nikolai, you have another question, please. Go ahead.
Yeah, that's a beautiful bridge to my question, which is also referring to your motto, Elmar, of Wetsus, combining scientific excellence with commercial relevance. I'm thinking about the electrified society that we're building now, and what comes to mind is the power to X term. You know, we have all this electrical power now from wind and solar and so on, and we need to create organic compounds that we used to create from petrochemicals before. I'm just speculating now, and I'm just asking you to speculate. Do you see any relevance for the principles of the water bridge being applied in the power to X technology? I feel the people that I talk to, they just, oh yeah, we are putting electricity into these H2O molecules that are a little bit, we don't know so much about them, and then we hope to get some organic compounds out in the other end. Can we be a little bit more smart with this knowledge that you just presented?
You raised an interesting point, which is, can we charge water electrically? Now, I know many chemists that will say it's absolutely impossible because of the law of electroneutrality, which again is a law that should be applied to a chemical equation. Then it makes sense. But of course, physically, you can charge systems, and you can physically charge water so that it carries electric charge. We have shown that, we have published that, we patented that. Actually, in the water bridge, if you take out water from the anolyte during bridge operation, and you take an electrometer, you can measure a field of a couple of 1,000 volts per meter, and you see it slowly dropping over time. And you can also use this sample, put it into a special impedance analyzer, and then you can see the excess protons, how they are reduced by taking the electrons during the measurement. So that is possible. And we recently found out that we can also charge our water by charging nanobubbles in there. So what you can create nanobubbles, and their surface can be electrically charged. We have recently found there can be positively charged nanobubbles, negatively charged nanobubbles. We can increase the charge, we can reduce the charge. I'm now speculating, perhaps we have also oxygen or hydrogen from the electrolysis nanobubbles in the analyte catholyte. Nobody ever analyzed that. So that would be interesting to see whether we have that and whether this is actually our charge carriers. And my point is, I think electrically charged nanobubbles can open a world to a new kind of chemistry and can probably be applied in industrial processes, because you can then, from flocculation to influence on calcium carbonate precipitation, you're adding charge without adding anything material, and that is interesting per se, because this is something you normally don't consider in chemistry, but it is certainly possible.
Great, thank you. Yeah, but I think that this is, I mean, we're just at the beginning of this field, and also the commercial aspects of this understanding. So,
and yes, and talking about nanobubbles, Rumiana, you were saying something about also the solid phase being present in water. In my opinion, the shell of the nanobubbles, there are some beautiful papers that they're actually ice-like. And so,
Yes,
and
absolutely.
the center is a gas. So I just wanted to say, I agree
Not
with
right.
you. I agree with you very much that also in liquid water, we might have the three classical phases, liquid, solid, and vapor in the liquid phase. And in addition, probably the electrically stressed phase. So just
And
because
many
we're talking,
others. And
this is
many
what I
others,
was thinking
most
about when you
probably.
and many more. Yeah. And this is what
Yeah.
I was thinking about when you mentioned that. So I fully agree with this too.
Yeah.
Okay. Anyone else? Questions? Raise your hand. Otherwise, I'm starting to speak. Again, it is very interesting. You mentioned nanobubbles. We did a lot of work with nanobubbles, different gases, and it was really interesting. We didn't publish it yet, but it is what we saw, for example, in these results. We saw that nanobubbles of certain gases have very nice protective properties, like antioxidative properties or radioprotective properties, and the Professor Tenkova actually mentioned this. The structure that was forming around these bubbles is this water solation shell that she mentioned. And interestingly, for example, we found these water solation shells also being a main characteristic of electrolyzed water, electrolyzed hydrogen water. So it's like origin of this ice.
Our papers on the subjects are also at the moment under review, so don't look for them yet.
Oh,
but we have a couple of papers on charged nanobubbles, which are now hopefully being published soon.
Anyone? Questions, please? Comments?
Just a comment. We try to take the energy out of the water, which is, I think, a wrong way. We just have to use the water in an intelligent way, so that we can directly use the energy within the water. And this is what you showed perfectly, actually. And I like very much that you pointed out the joint existence of photons and phonons.
Yeah.
And I think this is the way for our Aquaphotomics Society, and for really people that want to learn more about water, to go down to photons and phonons, because this is the basic.
Yeah.
And understanding the interaction, I mean, the next step will lead us to the protons and the proton wires in the system that are actually a result of the water restructuring. Yes.
Exactly.
And how water actually works. This is the way. This is the path that we can walk, and we have a lot of knowledge now out there, and papers that can help everybody that is interested in this direction. Thank you very much for pointing this.
Thank you.
Really, and for the wonderful.
Yes. Thank you, Professor Tenkova. Thank you, Rumiana. This is fantastic. I remember this moment of epiphany when Giuseppe Vitiello was standing in front of me. We were discussing vibrations. He said, but Elmar, in water, you have a dipole. If you have a vibration, what is moving? The charge is moving. So you have an electromagnetic field. You have a photon always. I was thinking, oh, of course, it's coupled. It's intrinsically coupled. It just goes together. You cannot separate it.
Yeah, and I think we have to be clever and stop thinking about electrical field. It is always electromagnetic. It is always,
of course, Maxwell
field, and it comes exactly because of what is a dipole.
Yeah,
and all the things that we know about water related to magnetism.
Yeah.
No, so
agreed.
Electromagnetism. Yes.
Yes.
Okay, anyone else? Some questions or comments? Okay, then we can maybe slowly start to wrap up. Elmar, do you have maybe something that you, I don't know, that you didn't get a chance to say or comment, or maybe you can ask questions? No?
No. I'm happy. I would like to thank you very much for pointing out the way we do research, and this is what we're doing with the water bridge at Wetsus. We're also doing with magnetic treatment, and magnetic treatment led us from the Lorentz force, which probably is not really relevant for most of the magnetic devices. It's too weak. To the idea of Professor Coe with the dollops. I don't know if you
I've heard about that. Wow.
Yeah, when we have the spins. And in 2020, and then recently, one of my PhD students, Tali, came up with the idea, it's actually bubbles, and the nanobubbles should be more important for calcium carbon precipitation. And I said, yeah, who knows? It could be. In 2024, in ACS Omega, Professor Coe published a paper about the role of nanobubbles and dollops in calcium carbon precipitation. And now we change our mindset again. And but like this is for me the most important way to work as a scientist, is to look at the data, stick to the data, and if the data tells you something different than your theory, you should change your theory. This is the way I have always been I've been working, and this is how we got from our original water bridge research to the coherence domains, because this was at this point, this is the most logical way to explain it, but it's probably not the end, or probably not everything that is necessary to understand the water bridge. And in magnetic treatment, as I told you, we're doing the same. At the moment, we think magnetic treatment has mostly to do with nanobubbles, but we'll see whether this is true or not. We're planning to continue with this.
Yeah,
and if anybody has a clue on why water properties would change during solar eclipses, please let me know. As you know, we also published a paper on that, and we have tested all hypotheses in that paper, and they're all wrong. So we're back to square one, and in 1.5 weeks, I will go to Mexico to the next solar eclipse. But the data is the data. The change in properties is there, but the physics remains to be understood. So.
Such an enigma. Christ. Wow, it sounds so exciting. Yeah. I have just one little comment. I don't know, maybe it's not even important, but I like it how you showed that protons are so important for me, from what I've seen so far in our work, for me, from my understanding, protons are a major life force. So that is what I would like to just comment. So I'm monitoring everything that comes about protons. And
I remember Adam Wexler. Some of you might know Adam Wexler.
You mentioned.
Yes. Yeah. He was a PhD student at Wetsus before he was in Jerry Pollack's lab, and he's told me he thinks protons are the currency of life.
Wow. So I'm not solitary. That's good. Yes, I love it. But I must add, I'm a little bit disappointed currently, because I was hoping that there is one part of near-infrared spectra that I think that, gives me best information about protons. However, since I consulted with some people who had this experience, there is one area called combination band. Unfortunately, I still cannot get a good quality spectra in this region of combination band. So I was very, very unhappy this maybe last 2 weeks when I was, because I thought that I will obtain very good high quality spectra, but then no. So I'm still sad. That is like a fresh wound in my heart. But I'm so interested about protons and how to find. I think that I can find it from combination band and near-infrared information about that.
I hope so.
Yes. Okay, so I think that we can maybe now say our goodbyes. Elmar, thank you so much.
Yelena,
sorry. Yes.
Yelena, I just want to Elmar to wish you a good luck in Mexico.
Thank you.
I would propose, Wetsus is a wonderful institute, and I wonder why you still don't use near-infrared spectroscopy and aquaphotomics for your water studies. I wish, and I would offer you to send to our lab your young colleagues to study aquaphotomics, because and we can give you an instrument, a portable near-infrared device to analyze the water when you go and analyze the water at this time.
Solar eclipse.
Yes, the solar eclipse. And because we have studied the changes of the water following the moon phases.
Oh, you
And there
can
is-
see that.
Yes, and we saw
Wow.
beautiful, beautiful correlation. Of course, it depends on the water very much, but we have seen that. So it's definitely, there is water is everywhere. And we follow Weber now, telescope, all the spectral data that sends to us, and all the spectra, they have, of course, the water bands that we have discovered. So there is water with same structures as the water we know on Earth, and it is a very, very important path in science to follow, I think. So let's teach, especially young scientists that are starting, and because knowing the water is just a tool. They could be biologists, they could be chemists, they could be physicists, and the knowledge about water is the background. It will help seeing the science from a different angle, and probably multiply the results of science. So I'm sure that you have done such a wonderful research, and now you are on a management position. So I think this is something that we can work together and for mutual benefits. Thank you very much.
Well, thank you very much for this offer. I'm deeply honored. Domarigato gozaimasu, thank you. And I would be happy to initiate a collaboration. We'll
Wonderful.
stay in contact about this. Yes, thank you
Yes.
very much.
Thank you, Elmar.
Thank you, Elmar.
Thank you,
Well, that
Elmar.
would be very nice to see. Thank you once again for coming today to do this lecture. And as I said before, again, it felt new, even though maybe I heard this, it felt new. I maybe in the meantime, I understood better some other things. Thank you, all of you, for attending and for asking interesting questions. It was really nice to have this beautiful discussion. I'm sorry that Pierre left. Pierre just left comments, and then when I asked him,
Yes.
he was not here anymore. As I said, the webinar is being recorded and it is going to be available on YouTube in a few days. You can then also use Japanese subtitles if something was not well, I don't know, understood by you. In the meantime, we wish Elmar good luck during solar eclipse. We keep our fingers crossed.
Thank you.
Hopefully we will hear some nice results this time and new theories and maybe good, like results with this.
Yeah.
And hopefully you can start learning also aquaphotomics.
Oh, yes.
Yes. Well, I think this is it then from us for today. Thank you all for attending. Thank you,
Thank you.
Elmar. Thank you,
Okay.
Professor.
Thank you all.
Thank you.
Thank you all
See you
very
then
much. It's
next
been a
month.
pleasure.
Thank you very much.
Bye bye.
Thank you.
Bye.
どうもありがとう
Bye-bye.
ございます。お疲れ様
Domarigato gozaimashita. Thank you.
お疲れ様です。
お疲れ様です。Thank you.